Okay, now you have access.
Good afternoon, everyone. I am happy to be here at the first International Society of Sets Extensions and Application Conference. My name is Soumyarani Pati, and I am a student from MS Department of Mathematics, Rajendra University, Balangir, Odisha. First, I would like to thank the conference organizers for giving me this opportunity, and I am also thankful to all of you for joining this session. Today, I will be presenting my work on project scheduling in uncertain environments and interstochastic Fauci approach to solve CPM. The main aim of the work is to develop the solution technique for interstochastic CPM. Next slide, please, ma'am.
Okay, thank you. You have 10 minutes. Okay.
Yes, ma'am.
Good.
Next slide, please. First, I am giving to introduce to you what is CPM and why we use fuzzy numbers to solve CPM. CPM, the full form of CPM is critical path method. The critical path method is a well-known method used for project management that schedules and organizes project activities. It identifies the longest dependent sequence of tasks, that is the critical path, which defines the project's shortest duration. Traditional CPM is deterministic, meaning activity durations are assumed to be fixed values without any uncertainty associated with them. There, obviously, there are many factors in the real world, such as resources, weather, and unforeseen delays that affect a project duration. Because CPM is unable to treat these uncertainty issues, it limits its use in project situations that are more complex. That's why Fuzzy CPM was created to provide the time duration uncertainties by using Fuzzy set theory to describe the uncertain activity durations. Fuzzy CPM does not assign exact values but describes activity durations using Fuzzy numbers. Numerous authors have suggested Fuzzy based methodologies to perform critical path analysis in project networks. In this slide, we discuss about the reviews relevant development in interstochastic Fuzzy CPM and compares them against the overall literature. The primary purpose of the article is explained below. The interstochastic fuzzy CPM is designed by extending the critical path method, utilizing interstochastic fuzzy sets to account for uncertainties in the durations and cost of tasks of project management. Interstochastic fuzzy CPM using triangular interstochastic fuzzy numbers adds an additional level of uncertainty as it better describes the vagueness which enhances the reality of project planning and established schedules. This study proposed two techniques for calculating the critical path based on varying levels of risk as it belongs to 0 1 close bracket. The possibility mean function is then employed to convert the interstochastic fuzzy activity into the relevant crisp activity. In this slide contains some necessary definitions related to the interstochastic fuzzy sets. First of all, fuzzy sets. Let X be a non-empty set. Then the fuzzy set contains a ordered pair X and X mu of AX, where mu of AX mapping from X to 0 1 close bracket is the where is the membership function of the fuzzy set A. Fuzzy set is a collection of objects with graded membership, that is having degrees of membership. And second one is interstochastic fuzzy set. Let X be a non-empty set, and interstochastic fuzzy set is consist of a order pair is X mu AX and VAX, where mu AX and VAX is define the degrees of membership function and degrees of non-membership function. And interstochastic fuzzy number is defined in the definition 3. Triangular interstochastic fuzzy number is defined in definition 4. And to solve the CPM, we use possibility mean function, which is defined in definition 5. This slide shows the essential notation in the Intuitionistic 4G CPM, which generalizes the classical approach to project scheduling by adding uncertainty through Intuitionistic 4G sets. This is the abstract diagram which shows that the Intuitionistic 4G CPM, for better understand the activities, are considered as triangular Intuitionistic 4G number. Then we discuss about two ways to solve CPM and algorithms. The CPM consists of two calculation: forward pass calculation and backward pass calculation. So this is the technique one for forward pass calculation. First, choose the risk factor delta belongs to 0 1. Calculate the possibility activity duration by using possibility mean function. The computation begins from the start node and moves towards the end node. For easiness, the forward pass calculation starts by assuming the earliest occurrence time of 0 for the initial project event. Earliest starting time of the activity ij is the earliest event time of the tail end event. Earliest finish time of the activity ij is the earliest start time plus the activity time. Earliest event time for event j is the maximum of the earliest finish times of all activities ending in to that event. This is the technique one for backward pass calculation. First, choose the risk factor delta belongs to 0 1. Calculate the possibility activity duration by using possibility mean function. For ending event, assume e equal to l. Remember that all is have been computed by forward pass calculation. Latest finish time for activity ij is equal to the latest event time of event j. Latest starting time of activity ij is equal to the latest completion time of ij minus the activity time. Latest event time for event I is the minimum of the latest start time of all activities originating from that event. This is the technique 2. In this technique, we solve Intuitionistic for GCPM. The first of all, forward pass calculation. Construct the 4G project network using Intuitionistic 4G numbers as activity durations and assign event numbers accordingly. Represent each Intuitionistic 4G activity duration in parametric form. Assume that the Intuitionistic 4G earliest starting time of the initial event is 0. Compute the earliest start time for each event using earliest start time is equal to max of earliest start time plus activity time. Using the ranking function, we choose the maximum value of earliest start time and compute the Intuitionistic 4G earliest finish time for each activity using Intuitionistic sorry earliest finish time is equal to earliest start time plus the activity time. For solving the backward pass calculation, assume latest finish time is equal to earliest start time. Since the Intuitionistic 4G latest finish time of all the end activities is taken as the earliest completion time of the project network. Compute latest finish time is equal to minimum of latest finish time minus the activity time. Using the ranking function, we choose the minimum value of latest finish time. The Intuitionistic 4G latest start time for each activity is latest start time is equal to latest finish time minus the activity time. Then calculate the total float for each activity. Total float is equal to minimum of latest finish time minus earliest start time plus the time activity. An activity is said to be a critical activity if and only if its total float is 0. This is the algorithm for technique 1. This consists of solution technique 1. Similarly, algorithm 2 is consist of solution technique 2. We include two numerical examples to demonstrate the applied nature of methodology. This is the network diagram of.
Miss Pati,
Yes,
you
ma'am.
have 1 minute more. Please conclude your article, please.
So by using solution technique, we can solve the CPM to solve the CPM, and by using the possibility main function, we calculate the earliest start time and the latest finish time for different values of delta. This one is the critical path for this example. By using technique 2, the critical path analysis is carried out for each value of delta belongs to 0 1 close bracket. Thus the critical path is 1 to 2, then 5, then 6, then 8, and then 9. This one is the comparison of activity duration using technique 1 and technique 2. For example 2, this is the critical path which is highlighted in the figure. And finally the conclusion. The suggested technique for addressing the interstochastic fuzzy critical path method effectively tackles the uncertainty and hesitation in activity durations using triangular interstochastic fuzzy numbers, conducting the forward and backward pass calculation method to determine the earliest start time and latest finish time, and calculate the total float for each activity. The developed algorithm demonstrated that the interstochastic fuzzy CPM methods can ultimately be used in real-life project scheduling. The sensitivity of the critical path was investigated by adjusting the risk factor delta to different values. When the risk factor is increased, the values of the earliest start time and the latest finish time decreased, indicating that there is even more uncertainty and hesitation in project scheduling. This suggested the need for selecting an appropriate risk factor delta according to the project situation and risk preference. For future research could consider the integration of alternate fuzzy number representation, utilization of MCDM project in scheduling to help improve decision making, and consideration of integrating interstochastic fuzzy CPM with machine learning or artificial
Thank you
intelligence
very much, Ms.
adaptive
Pati.
in project scenarios. Thank you.
Thank you for your great presentation. Okay. Now, dear audience and dear Dr. Mohanta, feel free to ask question. You can write it in the chat box, or you can raise your hand.
I have a question. This question you have to validate with numerical example. Is there any practical example for this?
Yes, sir. In software line, we can solve in the real life.
Okay, thank you very much.